Now, and there's a lot in this chapter. This is section 8-1, I believe. 8-1? 8-1. And 8-1. And this is kind of a general overview of sequences and series, and we'll talk specifically about arithmetic sequences and geometric sequences and stuff like that. So basically, a sequence is a sequence. Am I recording? Yeah, I'm recording. So a sequence. What does this do? Do you guys know what this does? What if I hit that button? What does this button do? Go away. Please go. Go away somewhere. I don't know. All right. So a sequence is a set of numbers like 3, 7, 11. Oh, 7, 11. 15, 19. Okay. And you guys could probably recognize what am I doing in that sequence. I'm adding. Okay. So this is when you add, it's an arithmetic sequence, but we're not going to worry about that. But sequence, what's kind of different about a sequence is this is the term. So this is the term 1, 2, 3, 4, 5. Until you get to the nth term. And this you would call a sub 1, a sub 2, a sub 3, a sub 4, and so on like that until you get to a sub n. Okay? And so the difference between like a linear equation and a sequence is that a sequence is, let me just write that, unordered set of numbers where the domain is positive. Go away. Is positive integers. Okay? So integers. So you're looking for the first term, the second term, the third term, the fourth term. So that's like your input. Sometimes you'll talk about the 0th term, but usually you start with the first term, not the 0th term. So if you see a sequence like, let's change colors, kind of like that. If a sub n is equal to negative 2n plus 7, and they say write the first 4 terms. Could you do that? Stephanie?
Yeah.
How would you do that? What would be the first term?
Ones.
1. No.
Or 0.
No. It would be negative 2. You just plug in 1 here.
Well, that's
okay?
what I meant.
So negative 2 times 1 is negative 2 plus 1 gives you
5.
5. Okay, so the term, okay, if the first term is 5, the second term is, if I plug in 3, okay, and you can see this is basically, right, it's going down, right? And the fourth term would be
Negative
1. So this is the slope of a linear equation, okay? But the y-intercept, I guess if we went back to the 0th term, it would give you 7, right? But in this case, it's just a sequence of numbers. So that would be that. Write an expression. So then, a lot of times they, how about this one? What if I said, just to show you that they're not always linear sequences, you could have something like this. A sub n is equal to 3 times negative 1 to the n. And say write the first 4 terms. Could you do that? Yes, you could. What would, let's get all this junk out of the way. What would be the first term? 1, negative 3. What would be the next term?
3.
3. What would be the next term?
Negative
Negative 3. What would be the next term?
3.
3. That's kind of a weird one, huh? Because all that's happening in this sequence, this index is just making it switch signs from negative to positive, right? So that's a kind of an interesting sequence, but it is a sequence. Sometimes I like you to go backwards, right? Write an expression for the nth term, right? And expression if I have 1 over 3, comma 1 over 9, 1 over 27, 1 over 81, dot, 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 dot. What would the nth term look like? What's a sub n equal to? What would a sub n?
1 over 3 to the, wait,
What do you think?
It's a sub n minus 1 times 1.
A sub n minus 1 times 1/3. That'd be recursive. We haven't really talked about recursive yet. Okay, so as an explicit, that's not a 9, that's an 8. Sorry, my A sub n is so if I start with 1/3, right? Who can tell me? Try again. Explicit. Give me a formula finding any term in the sequence without looking at the previous term. Go ahead, Sam.
It's a sub n to the, it's 1/3 to the
1/3 raised to the n power, right? Okay, because if I take 1/3 to the first power, I get 1, and this is the first term. 1/3 to the second power, I get 1/9 one. So this could be 1/3 raised to the n power.
Could it also be with the 3 raised to the negative?
Yes, it could also be 3, or 3 raised to the negative n, which would be exactly the same. Okay. Okay. So that's that. You can do that, right? All right. Recursively defined sequence is kind of what. So these are called explicit. This is explicit. Explicit, meaning doesn't mean it has bad words in it or anything like that. Explicit means that you just if you want the 100th term, you just plug in a number for n and you get the 100 terms. A recursive sequence, okay? Recursive is one that recursive sequence depends on what comes before it, on what comes before. Kind of like what Sam was talking about in the last case, right? If I took 1/3, multiplied it by 1/3, I get 1/9. If I take 1/9, I multiply that by 1/3, I get 1/27, right? And so on and so forth. So, for instance, so here's a recursive sequence. Usually I have to be given the first 1 or 2 terms. So say a sub 1 equals 5, and a sub k is equal to 2a sub k minus 1 minus 3, where k is greater than or equal to 2. So instead of using n here, they use k as the number of the term. So what this says is take the first term. So if I say write the first 4 terms, okay, with this recursively defined sequence, you start with the first term, which is 5. And then you multiply, so this is the next term, which is a sub k, is the previous term, this means the previous term, times 2 minus 3. So what would be the next term? 7. You see that? Okay. So if I take this term, so this says, if I want this term, I look at the previous term, multiply it by 2, and take away 3. What would be the next term?
11.
Would it be 11? 2 times 7 is 14, minus 3 is 11. And the next term would be 22 minus 3 is 18. Is that right? Did I do that right? I think I did that. 19? 19. I didn't fix that. Uh-oh. Okay? So you get a recursive sequence. That's recursive. There's a very famous recursive sequence that looks like this. 1, 1, 2, 3, 5, 8. What's next? 13, 21, 34. Okay, who knows what that's called? That's called a Fibonacci sequence. Good. Numbers or sequence. And what's the pattern? Who could give me a recursive definition of how to find it? What's a sub k? A sub k. Well, first you have to start with a sub 1. What's a sub 1? What's a sub 2? 1. And then a sub k is equal to the previous two terms added together, right? So it'll be a sub, we'll call it k minus 1 plus a sub k minus 2. You guys get that? Where k has got to be greater than or equal to the third term. Because you can't start with the second term because you don't have two terms before that, right? So you have to start with the third term, and then you add that says add the two previous numbers. You get that. Turns out we're going to explore some of this next week. I have some activities for it and stuff. But it turns out that there's all kinds of interesting patterns in Fibonacci numbers, and there's ways to solve probability problems using Fibonacci sequence, and there's all kinds of interesting patterns. So, get that? Easy? All right. You guys know about factorials? There's a lot of stuff in here. Okay? So, factorials, like, and these come up again a lot in probability and counting principle and even in binomial theorem, which we're going to talk about towards the end of the chapter. What's 5 factorial mean? No, it doesn't mean 5. It means 5! You know, like exclamation. No. No, it does. That's right. Austin was right. So 5 factorial means 5 times 4 times 3 times 2 times 1, which I think is 120, isn't it? 120. Okay? Which use, and you use factorials a lot when you're counting up things or you're figuring out how many batting orders there are or something like that. So if you want like n factorial, that's equal to n times n minus 1 times n minus 2 times n minus 3 times dot 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 until you get down to 1, right? And by definition, to make everything work, 0 factorial has to be equal to 1. Just otherwise, things don't work out when you're dealing with factorials. Okay? So you do factorials. So you could have sequences involving factorials, like write the first 5 terms of a to the n. A to the n is equal to, whoops, not a to the n. A sub n is equal to 2 to the n over n factorial. So the first term would look like 2 to the 1 over 1 factorial. What's that equal to? Did I do that right? Yeah. Over 1 factorial, and that's just equal to 2. The second term, so this is first. Second term would be 2 to the 2 over 2 factorial. Did I do that right? Yeah. Which is also equal to 2. Do you guys see that? 4 over 2? So that's the second term, but it's not always equal to 2. Because after that, the third term is going to be 2 to the third over 3 factorial, which might take you, what's 2 to the third? What's 3 factorial?
6.
3 times 2 times 1, which is 6. So this comes out to be 4/3. Okay? And the fourth term would be 2 to the fourth. Let's just stop after the fourth one. Over 4 factorial, which is 16. Over 4 times 3 times 2 times 1, which is 24, which comes out to be, divide both by 4? 4, 2/3, right? Oh, you can divide both of those by 8, right? That's 2/3. And so this is a sequence that it appears will go to 0 after a while. Okay? Yes? No? Simplifying factorials. I only did the first 5. So let's change it. There. Simplify factorials. So to simplify factorials, say you have something that looks like this. 8, and these come up a lot when you're talking about computing probabilities or combinations and permutations and stuff like that. Wouldn't you know how to do that? Have you guys ever seen factorials before? Have you ever done this? Like this kind of stuff? Okay. So to simplify something like this is equal to 8 times 7 times 6 factorial on the top, right? Because this will keep going, 6, and then you have 6 factorial on the bottom and 2 factorial on the top. So now what could I cancel out?
6.
You could cancel out the 6 factorials. And what's 2 factorial? 2, and 2 goes into 8 4 times, and you get 4 times 7, which is 28. And that's a very useful technique, okay? Because if you're trying to do something like 100 factorial over 98 factorial times 2 factorial, which you might have to do, if you try to put 100 factorial into your calculator, it's probably going to give you an error because your calculator can't handle that much, okay? And if you try to divide that by 98 factorial, so you don't want to do that. You want to do 100 times 99. 98 factorials will cancel out and you get 50 times 99, whatever that is, okay? So, so you got to be kind of smart about that. And then where it gets really confusing is when you're simplifying factorials, where you just have something like this. What if I had n factorial over n minus 1, n factorial over n minus 1 factorial? How would I simplify that? What's that equal to? That, and what happens? So this is equal to n times n minus 1 factorial, right? Because this is, if this were 10, this would be 10 times 9 factorial over 9 factorial over n minus 1 factorial. And what could I cancel out from the top and the bottom? N minus 1 factorial. So this is just equal to n. Okay, so sometimes it's just variables. It can get a little bit confusing. Okay, like that. So n factorial over n minus 1 factorial is just equal to n. Okay. Done with that? There's more. There's more. I'm going pretty good though. Okay. Let's take a break. That's really sweet. Okay, so the next thing that they talk about in this chapter, and there's a lot of just kind of knowing what things are called. Summation notation. And I'm not going to teach you any of the calculator stuff yet, but we will. So summation notation, you know that this thing means a sum. Do you know that? That's a sigma, which is is that a Greek letter? I think so. So that's called sigma notation. And so if you have something like this, I equals 1, 2, 5 of 3i, okay? This thing is called the lower bound. Lower bound. And this thing up here is called the upper bound, or sometimes the upper limit. Upper bound. And this thing is equal to, what this says is take 1 and plug it in here, then take 2 and plug it in here, then take 3 and plug it in, then 4 until you get to 5, and then add them all up. Okay? So that's what this says. So what would be my first term of this sequence? What's 3 times 1? 3. What's 3 times 2? 6. 3 times 3? 9. Okay. 3 times 3 times 1, 3 times 2, 3 times 3, 3 times 4 is 12, and 3 times 5 is 15. Maybe at the end I'll show you how to do this on your calculator. And so if you add those all up, 9, 18, 30, 45, right? So that's what that means. It says take all the numbers and add them up from 1 to 5. All right. Here's some finite series. We'll talk about that. Properties of sums. Properties of sums. Properties of sums. So the sum of a constant sequence from 1 to n of c, where c is a constant, is equal to n times c. So what does that mean? That means if this number is a constant, all I really have to do is take this top number and multiply it by that constant. For instance, say I want the sum from I equals 1 to 6 of 2, right? So what all that's saying is I want to take, this number is always a constant, so I take the first number, which is 2. I add the second number, which is also 2. I take the third term, which is also 2. The fourth term, which is also 2. The fifth term, which is also 2. And the sixth term, which is also 2. And I add those all up. And all I really had to do is go 6 times 2, which gives you 12. You see? Okay, so if this number here is a constant, and this is starting at 1, all you have to do is multiply that, multiply whatever the constant is by that number. Yeah?
Oh, if there's not an I next to the constant.
This, from I equals 1 until I equals 6. No, that's not an I, that's an N. I'm sorry. That's an N. Okay? And then another property of a sequence.
Wait, why doesn't that work for the top one?
Because this isn't a constant. This is, so here you're plugging in numbers for I as good. Okay? Another property is that if you have a sum and the sum from I equals 1 to n of c times a sub I could pull, if this is a constant, I'm allowed to pull that constant through the summation symbol, and I get I equals 1 to n of a sub I. So if this is like 5, I don't know, 5 times x squared or something like that, or 5 times a squared, I could pull the 5 out in front, find the sum of the a squares, and then multiply through. So that's another property. Another property, just the last one, is that if you the sum of a sum or difference. So I'm going to write this like this: a plus or minus bi is equal to the individual sums. So I equals 1 to n of a sub I plus or minus the sum from I equals 1 to n of bi. Okay? In other words, if I have the sum of something that's a sum or a difference, I could break that apart into two sums. And these are exactly the same as properties when you get to calculus next year. They're exactly the same as properties for integrals. Because some integrals are nothing more than infinite sums of infinitely close together numbers. All right. So anyway, so those are some summation properties. Almost done. Okay. So a series. So they talk about sequences and series, kind of in conjunction. And a series is the sum of a sequence. So we just saw some sequences. Whenever you're talking about a sum of a sequence, you're talking about a series. And so then we have something called a partial sum. So a partial sum is, or series, is one that has a finite endpoint, okay? And so it ends. And an infinite series, okay? Guess what's true about an infinite series? Infinite series or sum doesn't end. So for instance, an example of an infinite sum is, so say I started from I equals 1. I equals 1 to infinity of 3 over 10 raised to the I power. And they say find the third partial sum. And then they'll say find the infinite sum. And you'll say, how can you find a sum if it's infinite? Fine, but it's kind of cool that you can do that. And that's what Mrs. Hine is teaching in Calc PC right now. And infinite sums could be very, very complicated if they're alternating back and forth and doing different things. But we're just going to talk about it in pretty straightforward terms right now. So what they mean by the third partial sum, they mean add together the first 3 terms of this sequence. Okay? So what would be, so if I wanted to do this, what would be the first term? 3/10. What would be the second term? 3. This is going up to what? 2, so it's 10 to the 2, so which is 100. Plus 3 over what? 1,000. Does everyone see where I got that from? See, that's 3 to the, that's 10 to the first, 10 to the second. So if I add those together, I get that's 0.3. What's 3 hundredths? 0.03. What's 3 thousandths? 0.003. And if I add those together, 0.333, right? That would be the third partial sum. What would be the infinite sum? If I added those up forever and ever and ever and ever, what would I get?
3 repeating.
I would get 3 repeating, which is just what? Exactly 1/3. So the infinite sum, okay, find the infinite sum would just be 1/3, right? Because it's point, right? Because even though I'm adding things together forever and ever and ever, I'm just adding things at the end of the decimal place. So eventually that's going to be almost exactly, it is going to be exactly 1/3. So it's kind of weird that you're adding together an infinite bunch of numbers, but eventually you're getting to 1/3. Another way I like to think about that is say, can I draw a rectangle here? Say we have a rectangle. I never did that before. So say I want to add up 1/2 plus 1/4 plus 1/8 plus 1/16 plus that. What do you think that's going to hit eventually? If I add up that sum. Well, look at it this way. If I take this rectangle, I'm going to take 1/2 of that rectangle. Then I'm going to take 1/4 of that rectangle. Then I'm going to take 1/8 of that rectangle. Then I'm going to take 1/16. Then what am I going to have? 1/32. Then 1/64. Then 128. Then so eventually, what's the infinite sum? Not 0.9 repeating, just 1, right? It's eventually going to approach 1. Okay? So that's kind of an interesting. All right. I guess since I have time, do I have time? How much time do I have? 10 minutes? I'm going to just show you how to do a sum on your calculator. First, I can do that. So say you have something, but there's a lot of homework to do. But I got through it. So, so first of all, say, I guess there's other ways to do this. Like you could go to mode, and you could go to, I might show you how to do this tomorrow. This is how you enter a recursive. You have to choose this sequence mode, and then if you go into your y equals now, look at what it gives you. It gives you, this is your first term. This is what you're doing to that first term to get the next term. So this says take the first term, multiply it by 1.01, and then subtract 100. This is like a amortization formula that I did last year, I think. And then this was, oh no, this says start at term 0, and this is the initial value. But we're not going to use this. We're just going to go to mode, function. And I didn't know this. Mr. Beamer told me this. So if you could go to math and 0. Look at that. That gives you that little summation symbol there. So say I wanted to do the sum of x squared terms from 1 to 5. Okay? So I'm going to first plug in my formula, x squared, comma. I'm going to go from 1 to 5. Okay? And then you have to tell it which variable you're summing up. So what this says is I want the sum of the sequence of all the x squared terms from 1 to 5. And again, how I got here, I used the math, then 0. Let's see if this works. It says go to. What did I do wrong? I think I have to do x first. X.
Stored as x at the end.
No, you don't have to do anything fancy. 1, 2, maybe I don't even need the x. Let's see. Sum of x squared, value paired for x. There it goes, okay? So what I just did here, I added up 1 plus 4 plus 9 plus 16 plus 25. Right? Okay, that's this. So going back again. Okay, I went math 0, and then I plugged in my formula, and then starting at x, and then going from 1 to 5. See? And you could look. Let's see if it gives you a table. Oh no, I'd have to put it into y equals to get a table. So if I wanted to put something like that into
How would you do infinity?
infinity. Well, this one doesn't have a.
Well, like,
It goes to infinity, right?
let's say, like,
All right,
infinity.
So resume the thing. Okay, so here's your rather large
Oh no.
homework assignment.
I just like
I think after this, there's so much terminology, it should get a little bit easier than this, but pre-calc assignments, chapter 3, chapter 8. There it is. I try to keep it plain, simple, white, so you can see everything. And those are the problems that I chose for you. All right.